Hi class. I cannot make it to the review tomorrow. I'm having some medical thing done and I'm not going to be able to be there in class. So my apologies. So here is the exam, and what we're going to do is go through it one piece at a time, and hopefully this works as well or even better than an in-class review would have. So this is the exam, and it's fall 2014, Strength of Materials Exam 3. This is under content on Brightspace. I went over this first problem yesterday, so I'm going to skip that for now and going to go over starting with problem number 2. Right? And this is the allowable torsion problem. So as you may recall, with torsion, and when you see a torsion problem, you're going to want to S sub S torsion equals TC over J, right? Remembering that C, right, is going to be the distance from the neutral axis to, right, that's the neutral axis there, distance from the neutral axis to the extreme fiber. J is going to be the polar moment of inertia. J equals 2 times I for this particular pipe, 102 millimeter extra strong pipe. And the torsion has to do with this piece up here. You may recall that T equals P times L, right? Where L is what we're going to be solving for. So you could rewrite this equation like this: S sub S torsion equals P times L instead of the T times C over J, and then we're solving for L. So ultimately L is going to be equal to J times S sub S torsion divided by C times P. I think that's about right. So now we just need to populate these variables in such a way that we have good units. So let's see, so we need S sub S torsion, and that's going to be an allowable, right? Allowable is equal to, up there, 273 newtons per millimeter squared. Very nice. Then we have, we're going to need to look up some information about that 102 extra strong pipe. So I've looked up the information. This was Appendix B, and the I and the J, that was also Appendix B. Make sure you look under extra strong. And it says stainless steel, but we don't really care about the material because all we're calculating at the moment is the loading. So ultimately we calculate the L, which is this equation we solve for up here. Down here, and we end up getting an L equal to 0.37 millimeters. Actually, we need 3 sig figs, don't we? Let me fix my spreadsheet here to give me that. Well, where's that? Okay. Anyway, we should end up with, now 0.37 millimeters is very small. So you may have noticed when I said 76,500 kilonewtons sounds like too much. That should have been newtons, but that's a mistake I have on the exam. So anyway, that's the answer you get. So that's what you report. And let's say the last digit is 0.370 millimeters. So when you're going to include your units, and that's a maximum. And of course that's a maximum because if you made your torque arm longer, right, you would be imparting more torque, right? P times L. If you have more torque, you're going to have more stress. The stress value we're using is a maximum, isn't it? It said it can only take 273 megapascals. That's what an allowable is. So that's the maximum. So if that's a maximum, then these over here are maximums as well. Anything in the numerator on this side is going to be a maximum. Anything in the denominator is going to be a minimum. Okay, so if the torque arm gets bigger, you make more stress. If the pipe diameter gets bigger, you make more stress. And that's what this last question is too, is the diameter of the pipe a max or a min? It has to be a max. Now this, of course, had a mistake in it. And I think when I gave this exam, I said, oh, by the way, that should be 76,500 newtons, or 76.5 kilonewtons. So feel free to ask those kind of questions in class. Yeah, that's what we have. So let's move on. Okay, so we have problem number 3. Steel channel is welded between 2 rigid, unyielding walls. So both ends are fixed. Okay, so it's welded to both sides. At 55 degrees, the member is experiencing 2 ksi of compression. Okay, so we could say, and let's go ahead and set up our temperature line here. Okay, and we're saying at 2 ksi, 55 degrees Fahrenheit, we got that much compression. Calculate the stress when it goes down. Okay, so I'm going to put 55 degrees Fahrenheit right here. So here's 55 degrees Fahrenheit. And this is on top is going to be the temperature and degrees Fahrenheit. And the bottom of this line here is going to be stress. So we'll put stress, and this will be in KSI. Okay. So we're saying at 55, it's feeling 2 KSI compression. Okay, I'm going to put C there. Calculate the stress in the member when the temperature changes to 32. So we want to find out at 32 degrees Fahrenheit what is going on. Okay, what is the stress? Okay, so this is our favorite thermal equation. So our equation is S therm is going to be alpha times E times delta T. Okay, so we're going to need alpha for steel, and this is steel, it says here. So steel, the alpha for steel, which is the coefficient of thermal expansion, is, and you'll see for all structural steels, is 6.5 times 10 to the minus 6th, and it's per degrees Fahrenheit. Right? That's the whole. Remember, this is the one with the unit only in the denominator, which is kind of weird, I know. Okay, E, we know this so well, 30,000 KSI, and our delta T is going to be our T naught, in this case minus T final, which is going to be 55 degrees minus 32 degrees, which is going to equal to 23 degrees Fahrenheit. So there we can figure out what is our stress. And really what we're finding is our change in stress, aren't we? Because we have an initial stress of 2 KSI compression, and what's going to happen when the temperature goes down, right? So when it goes down, what does this want to do? Does it want to shrink or expand? Correct, it wants to shrink. So if it wants to shrink and it cannot, is that going to be causing more tension or more compression? And I think we all agree that that's going to cause more tension, right? It's trying to pull apart, but it cannot. It's trying to pull closer to the center, but it cannot. So that's the same thing as if the walls were trying to pull it apart, and it wouldn't move. Of course, it was attached because it's welded. So it's going to cause more tension. So we're going to find that this change in stress will be in the tensile direction. So we'll say the change in stress thermal is equal to 6.5 times 10 to the minus 6th divided by degrees Fahrenheit. I'm just going to put it down there because that's handy. Times 30,000 KSI. And kind of running out of room here, so we'll just put it over here. So I'm 23 degrees Fahrenheit. And of course, those are going to cancel, aren't they? So we end up with a delta S thermal, right? Remembering this is our change in stress. What did I get? 4.49 KSI. And remember, that's in the tensile direction. Oops. Tensile direction. Okay, and I'll even write direction here. So looking up here, we started at 55 degrees Fahrenheit. We made it down to 32 degrees Fahrenheit. The change was 4.49 KSI in the tensile direction. We started off with 2 KSI compression. So we're going to lower out of that 2 KSI compression, and we're going to end up somewhere in here getting 0 stress, right? Because we're moving in the tensile direction. And then we end up with 2.49 KSI tension, right? How do we do that? Well, we started off with 2 KSI compression, and we could consider that, say, positive, and say tensile direction negative. So then you end up with 2 KSI minus 4.49 KSI, which would give you negative 2.49 KSI, or just call it tension. So we're just going to say 2.49 KSI, and it says tension or compression, so you can circle it or you can write tension, right? But you need to specify, right? Okay, so now it's asking, at what channel or at what temperature will this channel buckle? Okay, so we already decided if the temperature goes down, we're moving in a tensile direction. So to buckle, we need, as we talked about in column design, we need to increase the temperature and cause compression, right? Because we're talking about compressive loading, right? So we need some information about our bar. Okay, we have a C 10 by 30 bar. So we're going to look that up in the appendix, and we're going to find some information. And I'll just tell you what we're going to grab. We're going to grab our area, just in case we needed a load, which I guess we don't need a load, do we? Well, we're going to grab it anyway. Area is equal to 8.822 inches squared, right? And this is appendix C, of course. And we're going to have an Rx and an Ry. Remember, we're going to take the smaller of the radius of gyration. In fact, let's talk about real quick what the equation is, because that's important, isn't it? So the equation for buckling, right, the Euler buckling stress is going to be, you're going to have KL over R squared in the denominator, and in the numerator we have pi squared times E. Okay? Those are all pretty simple things, right? Pi squared, interestingly, the only place I know about pi squared, it's usually just pi. E, 30,000 KSI, because we have steel again, it says so right there. K, right, has to do with our support conditions. And if you look in your notes, you'll see that K for fix is 0.65, because that's saying that our deflected shape is going to be approximately from here to here, which is about 65% of the initial length. L is going to be the initial length, but we're not going to use 20 feet, are we? We're going to use 240 inches. And our R, right? Remember, we're going to take an Rx and an Ry. We want the smaller value. Well, the smaller value here is going to be Ry. I didn't write down Rx. 0.669 inches, but know that Rx is bigger than that. We're not going to use it. Right? We don't care which direction it buckles in or across which axis. We just care that it buckles in this case. Okay, so what we need to do is find that stress corresponding with the buckling. So we crank through these numbers, and I'll write this out. So having written it all out, we have pi squared times E, 30,000 KSI, 0.65 times 240 inches. And notice we've got inches and kips, and we're doing really well. And Ry, by the way, is inches, so that's inches there. So these inches cancel. But 0.65 times 240 divided by 0.669, that whole thing squared. So that's often where the issue arises with calculation issues, is make sure you use your parentheses correctly and you square the entire denominator. And don't forget to square pi. We end up getting 5.45 KSI. Okay, so that's the compressive load at which we're going to end up buckling. So what we're going to need is we're going to need to find the delta T required to get us to 5.45. We know we started at 55 degrees Fahrenheit, right? We started up here. And we're going to get to some buckling temperature up here. All right, and we're going to figure out what that is. Turns out it's probably not going to be that much. So we're going to start off at, we're starting off at 55 degrees Fahrenheit, and we already have 2 KSI of compression. We need to get up to 5.45 KSI. So we need to find the delta T for a delta S thermal equal to the difference between 2 KSI and 5.45 KSI, so 3.45 KSI. In other words, when we get up to 5.45 KSI, that's an absolute, we're going to buckle. The change in stress we need to find is 3.45 KSI, and we're going to find the delta T associated with that. Okay, so coming up to this equation here, we're just going to rewrite that, solving for delta T. So we have delta T equals delta S therm over, make sure I get all that in there, delta S therm divided by alpha E. Right? And that's, again, just this equation here. That's our master equation, and we're just solving for delta T. Okay, so our delta S therm that we're talking about is 3.45 KSI to get us up to 5.45 KSI compression. So we say 3.45 KSI, and we divided by our alpha and our E, and our alpha we looked up very first thing, so that's 6.5 times 10 to the minus 6th per degrees Fahrenheit. And notice that we're in the denominator here. Degrees Fahrenheit's in the denominator of the denominator. That pops back up to the top. And then times 30,000 KSI. Right, and notice the KSIs. So we get 17.7 degrees Fahrenheit. That's our change in temperature. Right? Our initial temperature was 55 degrees Fahrenheit. So if we add those two together, we end up getting 72.7 degrees Fahrenheit is when it buckles. And if we filled out our little temperature thing up here, which you may be required to do, we're going to say 72.7 degrees Fahrenheit. Okay, and just for edification, if we were to have a little more detailed temperature thing, where we would say, okay, we know we had a 32 degrees Fahrenheit, and we know that that was the change in stress, and we ended up with 2.49 KSI tension. Then we had our 55 degrees Fahrenheit. That was our initial condition. We started off with 2 KSI compression. Yep. And then we said when we get up to 72.7 degrees Fahrenheit, we end up at our buckling temperature of 5.45 KSI, and that's compression as well. And this here is the buckling temperature, which isn't very high, right? 72.7, we even hit that around here. So that's what you get. And you know, it's somewhere in between here, and it's linear, so you can figure out exactly where it is. It's not quite halfway, but somewhere around there, you are going to have a zero stress moment. And you could also say at that zero stress temperature in between here, that's also where it was installed. See? Or we could say this is the temperature, when installed. Get it? When they installed it and they welded it in there, they didn't wedge it in, or they didn't move the walls closer together, or they didn't to put some compression on it. They basically said, okay, you put it in here at a certain temperature, and then when the temperature, when there was zero stress, when it just fit in there nicely, and then the temperature went up, and we got 2 KSI compression, and then it went down to freezing, and we got 2.49 KSI tension. And then if we went up to 72.7 degrees Fahrenheit, we buckled. So one of the reasons that happened, by the way, oops, wrong page. One of the reasons that happened, by the way, is because this is 20 feet long, and this isn't such a huge channel. So that's a very slender member, so it's easy to buckle it. All right, so problem number 4. You'll notice that what we have here is we have ourselves a 20 kip load going up at an angle, and we've got a 4-inch standard weight pipe. All right, so I'll put that here. 4-inch standard weight pipe, and you could even think of it as, okay, here's the walls that we can't see, but if we did have x-ray vision, we could see that this thing was hollow in the middle. It is a pipe. Okay, it's 10 inches long, so we have 2 loads on this thing, don't we? We're going to have a load, and I'm going to do this a little smaller up here, right? We have a load going like this, which is axial tension, and then we also have a load which is going perpendicular to that longitudinal axis, right? And that's going to give us a bending load that's going to cause this thing to sort of bend in that direction. So we know that this point B right here is going to be feeling a little more compression because of that bending, and point A is going to be feeling a little more tension because that's on the tension side of that bending. It's a vertical cantilever, yes? Okay, so this is our combined stresses problem. So here we have an axial load, and here we have a bending load, right? So the way I like to do that is just calculate the axial and then calculate the bending, because these are symmetrical on either side of that central axis, right? Our longitudinal axis, which is our neutral axis in this case for the bending. So we know that B, the amount of compression B will be feeling from bending, will be the same magnitude as the tension that A is feeling because they're an equal distance away from the neutral axis. Right, so we have M max times C over I sub x. Right, so that's our bending stress, and this is our axial stress. So we could say axial if we wanted to say it that way. Okay, so we're just going to need to calculate each one of these, and then we'll make our table. We're going to need a little information about our pipe. So what do we need? Well, we're going to need our I sub x, and we're going to need the OD. For our pipe, let's see, I have this here somewhere. Okay, OD for that standard weight pipe, and this is in Appendix B, is 4.5 inches equals OD, and we have an area. We're going to need that. I don't know why I'm doing it backwards like this, but hey, why not? 3.17 inches squared equals the area. And do we need anything else? No, we don't. All right, so we're going to figure out this M max, but we know that that's just a force times a distance. We're also going to need to calculate what our components are. So we have 82 degrees here. So we know, first of all, looking at this, 84 degrees is very close to perpendicular, isn't it? Or very close to vertical. So we know that the Y component is going to be pretty close to 20 kips, and the X component is going to be much smaller. So that's a nice thing to think about just going in, right? Just from a logic standpoint. Okay, and it turns out that we have what ends up being this vertical is going to be 20 kips times the sine, right? Sine of 84.2 degrees, and that equals 19.90 kips. That's our vertical load. Our horizontal load is going to be 20 kips times the cosine of 84.2 degrees, and that should be much smaller, and it is. It's 2.02. In fact, well, let's do the same with 4 sig fig. So we said 2.021 kips, right? So that gets us where we need to go. So our S axial is going to be, that's our load, 19.9 kips. 0 kips divided by our area, which is 3.17 inches squared. And so S axial equals, what do we got? I'm going to move over. So axial looks like it's 6.27 kips. Okay, and that's a tensile load, right? So everything in this pipe is going to be feeling tension. So that's tension all the way around. Okay, bending stress is a little different, isn't it? Let's first define our M max, which is just going to be our force times our distance. Our distance is 10 inches. So it's going to be force times distance, which equals 2.021 kips times 10 inches. Those are nice numbers, aren't they? Equals 20.21 inch kips. Then C is going to, again, equal OD over 2. And that's going to equal to, our OD is 4.5 inches, so there's 2.25 inches. And our I, oh, I didn't get I, did I? Oh, that's dumb. Our I equals, let's go back to the pipe. And our I looks like it's 7.233 inches to the fourth. Okay. 7.233 inches to the fourth equals IX. So 7.233, yeah, just making sure, inches to the fourth. So then when we calculate our bending stress, didn't leave myself a whole lot of room here. So S sub B equals 20.21 inch kips times our C, which is 2.25 inches, divided by 7.233 inches to the fourth. And looking at our units, we have inches and inches on the top. That leaves us inches squared. And we have kips on top, so we end up with kips per inches squared. That's a good thing. And for our bending stress, we end up getting 6.19 KSI. Okay, so we know that that's going to be compression. We mentioned over here that's going to be compression for B, and it's going to be tension for A for the bending stress. Right. So that's why I like to do a table. So in my table, I do move this up a little bit. S sub A. Yeah, that's okay. S sub B. I know it's going to be KSI. That's going to be KSI, and okay, and then we'll sum it up at the bottom. It'll be the summation, and we'll put axial here and bending here. All right, so and let's set up a sign convention of positive being tension and negative being compression. And you can flip that if you want, because you're going to just have to tell me in the answer whether it's tension or compression. Okay, so the first thing I'd like to do is put the signs in there. So I know that both my axial are going to be positive. They're both going to be tension, right? I also know that my one place in compression is going to be point B in bending. I wrote that right there. Right, so point B in bending is going to be there. So that will be negative, and that will be positive there. And now we can just use our two values. We have our axial value, and we have our bending value. Bending is going to be 6.19 and 6.19, KSI, KSI. And axial is going to be 6.27 and 6.27. So now we have to sum them up. And you look at S sub A, you end up S sub A, you end up adding them together, right? And you get 12.46 KSI tension, right? If you add those together. Look what happens when you add up B, right? Because B, being in compression here and tension here, is they almost counteract. And you end up getting, with enough sig figs, 0.0. And I have these sig figs because I did it on a spreadsheet. but I end up with 0.0803, and that's 3 sig figs. Right? So just make sure you have the ability to get it to 3 sig figs when you get to the end. So, and that ends up being positive as well. So these end up both being tension, but this one just barely, right? And that ends up being tension. So as we write these, we say 12.5 KSI, and we have to say tension, and the other one we have 0.0803 KSI, and we say tension. Notice I included my units here, and I said tension. So there's your deal. Right? You need to make sure you do that. Okay, so A36 steel, will this work for this pipe? Well, what are we looking at when we're talking about that? A36 steel. We're looking at stress levels. The stress level we end up getting, the highest one, is 12.5 KSI tension and almost 0 KSI. So A36 steel allows 36 KSI ultimate, and we typically put a factor of safety on that. So when we put the factor of safety on our 12.5 KSI, and you could say that's going to be 1.5. We could end up saying, okay, we're going to, maybe allow 2/3 of that. But 12.5 KSI is almost a third. We're not even we're a little more than a third of the way up to 36 KSI, right? SY equals 36 KSI for A36 steel. A36 steel. 12.5 KSI is much less than 36 KSI. So, okay with A36 steel. Right, that's the way you answer something like that. Right, that's where the why comes from. If you just say yes or no, that's worth 1 point. If you don't say why, or if your why doesn't make any sense, then you miss the other 4 points. So make sure you say something that is meaningful. Okay, so this last one is not on there, but it's a beam design, so I just made one up. So what we're going to do is we're going to figure out what is the most economical section for this loading condition. Okay, so remember what we have to do is we have to check bending, stress. We need to check deflection. And we need to check shear stress. Okay? So to do this, we need some criteria. So I will provide this for you, but we'll say something like SB allowable, and this is a material parameter. SB allowable for whatever we're going to use is going to be 24 KSI. Okay? S sub S allowable, because these are kind of out of order, but let's say that's 10 KSI, and let's say that delta max has to be less than or equal to, we could say, L over 360. Okay, so that's our design criteria, and they didn't exactly match up, but that's okay. This one goes with that, and that goes with that. Okay, and the equations, of course, that we're going to use is SB equals M max times C divided by I, which also equals M max over S sub X. And that's really handy when we're sizing, isn't it? Okay, delta max, we're going to use Appendix H. And I'm now taking Appendix H and I'm putting that over top of this, so you should be seeing that right now. And you'll see the equation for Appendix H. You see the equation corresponds to load case number 1, where we have a uniformly distributed load. And so we're going to have 5WL to the 4th over 384 EI. And you'll see I've written that down here. So that's our delta max equation, and then our shear equation for W section is going to be Vmax over dTW. And that'll be the last thing that we check. Okay, so let's first check the bending. So we'll get into the bending. Okay, and in the bending, we're going to use the SB, right? The bending stress equals M max over S sub x, and we're going to solve for S sub x. So S sub x is going to equal to M max, and I'll just do this line here, M max divided by S sub b, and we'll just use the allowable that we had up here. Okay, M max, as we go back to our appendix H, right? Where's mine? Oops. As we go back to our appendix H is WL squared over 8. Okay, so M max equals WL squared over 8. And as far as our W goes, we don't like the feet, do we? So let's go ahead and change that to 1 foot over 144, or excuse me, 12. I was squaring it, wasn't I? 1 foot over 12 inches, and 5 divided by 12 is 0.417. 0.417, and that's kips per inches, isn't it? Because the feet go away, and that's kips per inches. So our M max is going to equal to 0.417 kips per inches times our length, which will be 240 inches squared, right? So this is 240 inches. We don't want to use feet, divided by 8. Okay. So running through that number, we're going to say equals the 0.417 times the 240 squared divided by 8. And we end up getting 3,000 for the M max. 3,000 inch kips. Okay, so our S sub x that we end up with is 3,000 inch kips divided by 24 kips per inches squared, because that's our SB allowable. And we get 125 inches cubed. So going to Appendix A, we look for a section modulus that is greater than 125 and has the smallest second number. In other words, W18 by 71 has an S sub x of, let's see, W18 by 71, S sub x equals 127 inches cubed. So that would work. Let's see if we can find a lighter one. And we go up and we say, oh, W21 by 62 has a section modulus of also 127 inches cubed. So which one do we like? Let me make sure I got that right. Yep, I did. So either one of these will work, and they're very close, and that's nice, but we like the 62 pounds a foot better. So we're not going to use this one because it's heavier, so we're going to say try W21 by 62. Remembering that this is saying, okay, W21 by 62 satisfies our criteria for bending. But that's all it does. This got moved, it looks like. Satisfies our criteria for bending, and that's good enough for now, because that's all we've checked is the W is the bending criteria. Okay? So now we're going to move on and check our deflection. Okay? And we know that our delta, or first of all, our L over 360, we need to figure that out. 360 is going to equal to 240 inches divided by 360, which is going to equal to what? Let's see. Equals 240 divided by 360, and that's going to be a nice even number, 2/3, 0.667 inches. So that's all the deflection we can have in the middle. I'm going to move this up. Okay, that's the maximum deflection we can have. All right, remembering that we have a beam that is deflecting like that, where it's simply supported, and this distance here can't be larger than 0.667. Right? Okay, so remember that what I asked for you to do in this case is to solve for I. So we have a delta max equals 5WL to the 4th over 384 EI. Okay? So we're going to rearrange that and solve for the I, and since the I is in the denominator, delta max in the numerator, we can just flip. Right? So we can say Ix, and we're going to say that's a minimum, is going to be equal to 5WL to the 4th over 384 E times delta max. And of course, we're going to take that 0.667 and use that as delta max. So, that's going to be delta max. We know W is equal to the 0.417 kips per inch. We know that the L is equal to 240 inches. E, 30,000 KSI, because we're talking about a steel beam. And we know we're going to set delta max equal to 0.667 inches. So that should give us a value for our moment of inertia. What is our current moment of inertia? Well, we're trying W21 by 62, and the I value for that is, what, 21 by 62, where's I? Right there's I. And it looks like it's 1330 inches to the 4th. That's what we're working with so far. So we want to figure out if, given this criteria, and we set it equal to that criteria, will 1330 inches to the 4th work out? Okay? So let's write out the equation. Ix min equals 5 times 0.417 kips per inch times 240 inches to the 4th divided by 384 times 30,000 kips per inches squared times 0.667 inches. Well, what units do we end up with? Well, let's see, the kips cancel. That's nice. So we just have a bunch of inches here, don't we? So it looks like we have inches cubed on the bottom and inches. So we end up with inches divided by inches squared. So that would be 1 over inch, and that jumps up to the top. And we have kips per inch times inches to the 4th. So we end up with inches cubed plus that inch jumps up to the top. So we end up with inches to the 4th. So that's good. Always a nice exercise to do. And I will run through this number. So we end up with an I min equal to, let's put it here, Ix min equals 900 inches to the 4th, which is less than 1330 inches to the 4th for the W21 by 62. So okay in deflection. 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 Okay, so we're still on a W21 by 62. Okay. All right, so what have we done so far? We checked bending. And that gave us a W21 by 62. Then we checked deflection. And that said our minimum moment of inertia is equal to 900 inches to the fourth, where W21 by 62 had 1330 inches to the fourth, so we're still okay. So we're still trying W21 by 62. Our last job is to check shear. Okay, so as we check shear, we just remember that our S of S allowable is equal to 10 KSI, and that was given. And the way we calculate the S of S actual, we could call it, given our loading conditions, is V max over D times TW. So we're going to need some information about that 21 by 62. And we find out that for the W21 by 62, 62D is equal to, should be close to 21, shouldn't it? And guess what? It's exactly 21.0 inches. That's not always the case. Okay, TW is W21 by 62, looks like it's 0.400 inches. And Vmax, if you look in Appendix H, you're just going to see it's the value of the reaction. And the reaction in this case is we have 5 kips per foot times 20 feet. That's 100 kips. So each of these babies is going to be 50 kips. Okay. You can also think of it as WL over 2, which it says in the Appendix H. So this will be WL over 2, which is going to end up being 50 kips if you crank through that. So that's our Vmax. So just checking to make sure that our actual is not higher than our allowable. Let's see what the actual is. Equals 50 kips divided by 0.4 inches times 21.0 inches. And we get, I'm going to run through this on the spreadsheet really quick. 50 divided by 0.4, also divided by 21. And we get 5.95. 5.95. And that's kips per inches squared, which is KSI, which is less than 10 KSI. Okay in shear. And so our final answer is we were okay in bending, okay in deflection, now we're okay in shear. So our answer is use W21 by 62. And put a box for good measure. Now, some of you are probably thinking, you know what, I'm not going to rearrange this deflection equation, and I'm going to just solve for the deflection. It's going to be a requirement to tell me what the IX min is, because as you move forward in your design level classes, you do need to design for the minimum moment of inertia. In other words, you need to calculate that going in. So I'm making that a requirement, so don't skip that. Do use the procedure that I've shown you in class multiple times and that I just showed you here.